Hey everyone, we are looking at doing the derivatives of implicit relations, which is a phrase you've maybe not even heard. So first of all, this is called implicit differentiation, which is quite a mouthful. And the thing with a relation is it's something where you have x's and y's maybe mixed together. You may or may not be able to solve for y. Like in this case, 3x squared plus y squared equals 13. It's this ellipse right here. I could solve this for y, but because of that squared, I would get like a plus or minus because you have the top and the bottom. So we might not want to, or it's possible we might not be able to solve for y and derive like we normally would. Just as a little bit of a note, download the Desmos app because our calculators can't graph things like this, at least not easily or at all. And Desmos app can do it really nicely. And it can just do, it can do a lot of stuff and it's free. So the Desmos app is your friend. Okay, so we have this ellipse right here, and the way we derive this, some of it is going to be exactly like you've always done. Most of it, actually. The place where we have to really watch is the y. Like if I'm just deriving like y equals x squared, I know that the derivative of y is dy dx. That's not really news, is it? So, but this is something to keep in mind, and it's not something we put much thought into, but that the derivative of y is dy dx, or it's y prime. For implicit differentiation, I prefer dy dx notation, mostly just because they're more visible. It's really easy when you have a bunch of y's and potentially y primes, you could like mix them up and lose them. It's better to have them really obvious, so they stick out like a sore thumb that way. Okay. So if we want to derive 3x squared plus y squared equals 13, derivative of 3x squared, no big deal. We get 6x. Derivative of y squared. Now, here's where we have to stop and think. You might just be like, oh, it's 2y. Well, I'm going to throw this in parentheses. Okay, chain rule, right? Chain rule says derivative of the outside. That's here. The 2, and then chain rule also says keep the inside the same. So I have 2y. Now here's the tricky bit. Not really tricky, you just have to remember it and follow the chain rule. So I just did derivative of the outside while keeping the inside the same times the derivative of the inside. The derivative of the inside is dy dx. And then equals derivative of 13, which is 0. One thing that's super weird about these is that when people are concentrating really hard on their implicit differentiation, they forget things like that the derivative of a constant is 0. You would not believe how many 13s I've seen on a problem like this. Okay, so we used the chain rule here. Be really careful with that. And then our last step is to simply solve for dy dx. So I can subtract 6x from both sides. So I have 2y times dy dx equals negative 6x. I can divide both sides by 2y. So I have dy dx equals, I can reduce that, negative 3x over y. So for example, the point 2 comma negative 1, which is part of this relation, we can find the slope there, and we can even write the tangent line for it, and that's not bad practice. Let's do that. So at oops, that should be a negative 2 and a positive 1. Wow, where's my brain? So at negative 2, 1, we know our x's and our y's, right? Dy dx is going to be negative 3 times negative 2 over 1, or 6. And then our tangent line, just for funsies, tangent line is going to be y equals our slope, 6, x minus our x1, so plus 2, and then plus 1. And there's our tangent line. Okay, so that was our derivative. And if I wanted to, and like looking at that, 6 as a slope sounds pretty reasonable, doesn't it? And that, I mean, I know that my drawing is a drawing and not like a properly made graph, but close enough. Okay, let's look at another one. Deep breath. So it's this guy right here on Desmos. And it's clearly not a function. And xy equals natural log y plus x squared is my equation. This isn't something I can solve for y. even if I wanted to. So instead I have to be really careful and I derive it. Now notice I have this x times y, product rule. So we have u equals x, u prime is 1, v is y, and here's the kicker, be careful, v prime is dy dx. So watch that closely. So our derivative, x squared, u prime, which is 1, times v, so I get y, plus u, which is x, times v prime dy dx. So there's the derivative of this left side. On the right side, we have the derivative of natural log y. Derivative of natural log, remember, is 1 over. So 1 over, there's our derivative of the outside while keeping the inside the same, 1 over y, times derivative of the inside. The derivative of y is dy dx. And then finally, the derivative of x squared, we get 2x. So we very carefully derive, product ruling that xy. So we have to remember everything, product rule, chain rule, all of it. Not a thing to be messed up here. And then we need to solve this guy for dy dx. One thing you can do for quality control is to count your y's. This sounds kind of silly, but whatever. So I count my y's in the original function, 1y, 2y's. I have 2 y's. And then you go to your derivative and count your dy dx's. 1 dy dx, 2 dy dx. I sound like the count. So as long as those match, that's a good thing. Original function, I have 2 y's. Derivative, I have 2 dy dx's. Okay, so in order to solve for dy dx, I need to get the dy dx's on one side of the equation and then not dy dx stuff on the other side. It doesn't matter if I move to the right or to the left. You might compare notes with a friend and your answer might look a little different, but if you look closely, really they're the same. It's just that one of you went to the right with dy dx and the other went to the left. I'm going to move my dy dx's to the left. So I'm going to subtract this 1 over y dy dx from both sides. While I'm at it, I'll subtract the y from both sides. So I have x dy dx minus 1 over y dy dx equals 2x minus y. So I subtracted the y from both sides. I subtracted the 1 over y dy dx. So I'm closer to solving for dy dx. Now that I have the dy dx's to one side, if I'm solving for dy dx, it would be so much better if I only had one of them, even though I have 2 here. I can make it with 1 if I factor. If I factor dy dx to the front, so I have dy dx times x minus 1 over y equals 2x minus y. So now I have dy dx times a thing. So if I want to make dy dx all alone, I can divide both sides by that thing, the x minus 1 over y. So I'm left with dy dx equals 2x minus y divided by x over 1 minus y. And it doesn't matter that that's ugly and I have a fraction inside of my fraction. I totally don't care. I just wanted to make sure I got my dy dx alone. So again, I had to, product rule. I had to chain rule. I had to chain rule some more with my 1 over y dy dx being the derivative of natural log y. I had to solve for dy dx by getting dy dx to one side, get not dy dx on the other side, factor the dy dx out, and then divide by the other stuff. And here is my derivative. There will be a second video showing a couple more examples, and that's not a bad thing. There are further examples in our textbook if you read the section on, it's section 4.8, and it's pages 169 to 171. And reading those is a good idea because it will give you an additional couple examples. And more examples is better than fewer. You can also try AP Classroom and poke around there. There's lots of videos. All you have to do is look up implicit differentiation. It's in Unit 3.